I don't want people to get deprived. Okay, so those in charge of putting it, excuse me, those in charge of putting in charge, and so I'm introducing first speaker, Martin Kruzik, on the passage from nonlinear to linearized viscoelastic.
Thank you very much just for an introduction. I also would like to thank Arvier and Valerie for the invitation to come here. Yeah, so this is a joint work with Manuel Friedrich from the University of Münster, and yeah, so that's a kind of one part of our general program on you know, not making or not creating a new or designing new materials, not creating even new models, but kind of finding connection between two old models. So our goal is to show existence of a solution to a model of nonlinear viscoelasticity without inertial terms, so it's just quasistatic. And okay, so you have a linear model of viscoelasticity, you have a nonlinear model of viscoelasticity. They live together in parallel, I would say, and we are now trying to find connection between them. So if you linearize the nonlinear model, what happens? Do you get a linear one or do you get something completely different? And so, of course, we are not the first people looking at it, but I mean, for classical elasticity without viscoelasticity, this was already done in 2002 by Dalmaso, Negrin, Pacivale. And so this was an inspiration for our work to see whether we can do something like that also for viscoelastic materials. And I mean, if you have this, then you also are interested if there is some relationship between solutions to nonlinear and linear system. And so this is the last goal of our work, and now I will try to convince you that we succeeded in doing this program. So let me first tell you something about elasticity and how we put it. So it's kind of introductory because I expected a kind of more general audience, not really people just working in solid continuum mechanics. So for me, omega will be a reference configuration, so like a body before you do any experiment on it, and then y here is a deformation which goes from omega closure to R3. So there's the three-dimensional space. So I mean, you can also work in 2 dimensions if you want for simplicity or so. And then important quantity is the deformation gradient f. And this has a condition here that the determinant of f is positive, which is usually called orientation preservation, because it means that the, say, right-handed system and the reference configuration remains right-handed also after the deformation. And so to somehow capture action of forces on the body, we introduce the first Piola-Kirchhoff stress tensor, which is E for elasticity here, which moves from omega closure to the space of matrices, and it's a stress tensor which is living in the reference configuration, and it's a sort of a friend of the Cauchy stress who lives in the deformed configuration. And I mean, the relationship between these two tensors is through the Piola transform. And then you do some experiments, you introduce some forces through density of volume forces. You may also have surface forces if you want, but for simplicity, let's think about only volume forces here. And then the elasticity comes in, and this is a constitutive law for Cauchy elasticity, which says the first Piola-Kirchhoff stress tensor can be written as some function t hat depending on the gradient of y of x, and of course you can make it also x dependent and so on. If you do that, you derive the equilibrium equation saying that minus divergence of this tensor equals f, and you also prescribe some very clear boundary conditions on a part of your domain. So where gamma 0 is a part of the boundary, so part of the boundary. Now you can go also to a subclass of elasticity, which is called hyperelasticity, and it has a it has a special assumption, and the assumption says that the first periodic of stress tensor T has a potential. This potential here denoted by W is a function which is called stored energy density. And if you want to get a first periodic of stress tensor, you simply calculate partial derivatives of this function with respect to components of the matrix argument. Now, this function, from the physical reasons, has to satisfy some properties. So in particular, here 0 is not so important because it's like a potential. So if I add a constant, stress doesn't really change. But the important thing is that it's frame indifferent, which means if you multiply your argument f by rotation from the left, you have the same energy. So deformation followed by rigid rotation doesn't increase or doesn't change the energy. And this implies, and it's also equivalent, that W of f can be written as a small w function of ftf, which is the right Cauchy-Green strain tensor. So you immediately have this dependence. And then it's important property, which causes lots of troubles in mathematics, is that if the determinant of f goes to 0 from right, then the energy goes to plus infinity, which means squeezing a body to a point. Well, I mean, to do that, you require infinite amount of energy. And to make sure that your deformations are always orientation preserving, then you simply extend W by plus infinity if the determinant of f is 0 or negative. So that's elasticity or hyperelasticity. Why is it so nice to have hyperelastic materials? First of all, I mean, if you have this assumption on hyperelasticity, then you can write down the energy functional, which is phi of y. So this is the stored energy in the material, and this is the work of external forces. So for our case, we only have volume forces. And the Euler-Lagrange equations, or the equilibrium equations, are just Euler-Lagrange equations for this functional, but I would like to stress the word formally, because simply you calculate the Gateau derivative without really checking any assumptions, and you do it, and then you get equilibrium equations of elasticity. And then you search for minimizers of phi as solution to your Euler-Lagrange equations, just formally, and then this is possible to show that under reasonable conditions on W, you really can show the existence of minimizers. So the kind of nowadays standard condition is polyconvexity to John Paul, 1977, which means there is a convex and lower semi-continuous function H going from R19 to 0 plus infinity, such that W of f can be written as H of f, cofactor of f, and the determinant of f. So I just recall that cofactor are just is a matrix of subdeterminants 2 times 2. And you can also extend this notion to high dimensions if you want, or also to 2 dimensions. So this is well known, and for those kind of materials, if you have those conditions and so on, you can prove the existence of minimizers. So elasticity for us means you apply a force, and this causes some amount of strain or the deformation. So think about a spring. Applying the load on a spring, the spring extends or gets compressed and so on. So this is the main feature of elasticity. And if I release the force, the spring goes back. So now about viscosity. So stress is viscous stress depends on temporal change of the deformation gradient, and also possibly on the deformation gradient itself. So this is my stress S now. So it's a stress due to viscosity. Its S depends on F and F dot, so time derivative. And applied forces are proportional to the strain rate. So strain can be arbitrarily large if you apply the force. So think about a dashpot or damper. So somehow applying the force, the deformation gets larger and larger because you just control the time derivative. It's a different mechanism than elasticity. And so the standard assumption is that the viscous stress S has a dissipation potential. So the viscous stress can be written as a derivative of some function R with respect to the second variable, so f dot. So you have this formula, and for this function R, you assign the following assumption. So it's a non-negative function, and if the rate f dot is 0, then the function itself is 0. Now, similarly as we had frame indifference for the elastic energy, we also have frame indifference for this viscous stress tensor. And there is a quite famous paper by Entman from 1998 who somehow discussed various potentials for this viscous stress in the literature and showed that they are mostly wrong. And then he derived a condition which is a time-dependent frame-indifferent viscous dissipation potential, and it has to satisfy those conditions for every Q proper rotation in R3 and every skew-symmetric matrix A. So after some calculation, you come up with the formula that the R, depending on f and f dot, can be written as a function of C and C dot. So C is a right Cauchy-Green strain tensor, and so C dot is a time derivative of it. So here R plays a similar role in viscous materials as W in elastic ones. So this is an important property, which is physically important, but on the other hand, it causes lots of mathematical problems, as we will see. So now, okay, we have a dashpot or a damper and a spring, and then we can plug them either in a row, and then we get a Maxwell material because we have the same stress on both elements, but the strain sums up. And this is more like a fluid material, so Maxwell material. I want to talk about solids, so we put the damper and the spring in parallel, so in a column, and then we have a Kelvin-Voigt material, which means that the stress is sum up, but the deformation is the same on both elements. And of course, you can make lots of other models where you combine different springs and different dashpots, and you can create lots of rheological materials with this. So this is the idea that we have a Kelvin-Voigt material. So you write down the equation of equilibrium, so minus divergence of elastic stress, and the viscous stress equals F. And now the time dependence is important because the viscous stress depends on time. So I just say this is in the time space cylinder 0T times omega. And we also equip the system with initial and boundary conditions. So now, variational methods were quite successful and I would say very successful in continuum mechanics of solids. So one tries to write down the energy functionals and to look on the problem from the variational point of view. So we define the dissipation functional. So it's just the integration over omega of this R, this potential of viscous stresses. So just integrate over omega, and then we have this elastic energy function. So for us, these are two important energy functionals. One is responsible for dissipation, and one is the elastic piece. And so if you have it, so then just the formal calculation again shows that you can write down this equation as a gradient system where you calculate the R prime here is a derivative with respect to the second variable, and this is minus gradient of phi, so or that derivative of phi. So then the idea, which is already appeared in the literature before us, is to analyze the gradient system using semi-discretization in time as a sequence of minimization problems, and to see what happens if the time step goes to 0. yeah, so then we have some assumptions on viscosity. So this is similar as in Mielke, Ortner, and Sengier, who studied this problem first in the full dimension from the say, physical point of view, but then they were able to show existence of solutions only for one-dimensional situation. But yeah, I mean, this is just the idea. So you postulate the existence of some D, which goes from matrices with positive determinant, Cartesian product to 0 infinity, and satisfies DFF is 0 for all matrices. And then you associate the dissipation potential R as the following, by the following formula. So you take the D square, the dissipation distance, and then you calculate the limit for epsilon going to 0. And then you need the following assumptions on your D. So this is just, you postulate the existence of it, so we have some assumptions. So it's positive whenever the F1 and F2 have different right Cauchy-Green strain tensors. It's symmetric, it satisfies the triangle inequality, and it also satisfies the separate frame indifference. So if Q1 and Q2 are two rotations, then nothing happens with the value of D. So this is important assumption for us, and then you define the global dissipation distance and time discrete problem. So you just take the D square and then you calculate like the L2 norm of D, and this is your global dissipation distance. So now, if you have some capital T, your time horizon, then tau is a time step, and then you have some initial datum, so you define a sequence of minimization problems where the solution of a next one always depends on the solution of the previous one. So that's why you plug in the initial condition first. And so this is why, and tau is a argument of the minimum of this phi depending on tau, u and v, where u is a placeholder for the previous solution. And then you define this functional and you minimize it in a sequence. And so this looks like a good idea because you can say, okay, now I have the whole army of the calculus of variations which I can use to solve this problem. But usually, I mean, if you want to use the direct method of the calculus of variations, you need to apply some, or you need to verify some lower semi-continuity properties of the function. And this is what we want to do, and as already observed by Mielke, Ortner, and Sengier in 2014, the time-dependent frame indifference of D squared doesn't allow for polyconvexity of D squared. So if I have if I have an elastic energy which is polyconvex and this dissipation which is polyconvex, this would be super. But I mean, unfortunately, this is not the case. So this is a typical example of the viscous dissipation, which is like a distance squares of two Cauchy-Green strain tensors. This leads to R just depending on C dot in the power 2. And this is this function, if you fix one argument, it's symmetric in both, but fixing F1, for example, this is not polyconvex in F2. It has an even very bad convexity properties. It's very similar to, say, Sand, Venantilhoff elastic material, so it's not even rank 1 convex, say. So this is an issue, and I mean here you see, if I go back, that even if this is very nice polyconvex, and then I have this term which is not polyconvex, but the factor here is 1/2 tau, so the time step goes to 0. This term gets big way, and there's a danger that at some point you will lose polyconvexity or good convexity properties of this sum, even if this function is very nicely polyconvex or has some very good convexity properties. So this is already a problem which experienced Mielke, Sengier, and Ortner. So we decided to do a kind of a step aside, and it's to introduce the second grade materials. So these are elastic materials where the elastic stored energy also depends on a second gradient. So the idea goes back to 60s, to Mindlane, and also in Shilhavi 1997. There are many papers in Italian school, Polio, Guidugli, Caprice, and so on. So many people work on this idea, but it's a little bit controversial issue, I would say. So some people say this is kind of dirty thing. But anyway, we did it. So assume that you have also the second gradient of y available, and you write down your stored energy. This is the original stored energy density, but you plug in some little parameter and p of the second gradient, where p is kind of contribution to the elastic energy from the second gradient. So p is a convex function. You think about, for example, norm to the power 2 and so on, and then you write down the stress, which has now also contribution from this, as you take the derivative with respect to the second gradient. This gives you tensor of the third order, but then you take a divergence, and this is finally your first bilateral stress tensor. Mathematically, it's clear this second gradient brings more compactness to the problem. So once you have a convexity in the highest gradient, you really don't care so much about convexity here, just continuity say is sufficient, and so on. So the drawback of this approach is that I think there are not so many physical measurements which will tell you what kind of p you should take or what kind of epsilon you should consider. On the other hand, what we did is in our linearization, we also drive this epsilon to 0. So at the end, we get a standard linearized system. So this is just to get a solution for the nonlinear problem.
But can I ask you something? So if you take epsilon to 0, you're not going to get all solutions of the original problem, or do you get all of them? Because you are choosing some of the solutions. This is specific approximation.
No, you don't get, you get only some, no.
Okay.
Yeah, so this is now the new system, where also we have this kind of second gradient contribution, and yeah, and so again, I mean, now you say, okay, so this is the idea. So now we write the system for nonlinear viscoelasticity with the second gradient contribution and some delta, which will go to 0. So delta is a parameter in front of u of x. So we consider deformations of this form, so x plus delta u of x. And in our simplified setting, we assume some boundary conditions, just identity on the boundary, and then the parameter here in front of this term is such that it will finally go to 0. Yeah, and the question is what happens if you do delta goes to 0, the limit, and we also later on put f equals 0. So the heuristic calculation tells you, if you do just the heuristic calculation, that you get a system of linearized viscoelasticity. So it's a standard system where CW are just elastic constants, and CD are just coefficients of the viscosity matrix, and E of U is a symmetrized gradient of the displacement. So this is what you expect to get, but now you have to do the formal calculation. So let me just recall some recent work on viscoelasticity. I already mentioned Sengil, Mielke, and Ottner, but there's also work of John Ball and Yasemin Sengil from 2015, and the thesis of Yasemin Sengil. So the existence results in 1D setting and discussion about various viscosity potentials and quasistatic approximation. So the existence is via gradient flows in metric spaces, following the ideas of Ambrosio usually somewhere, I would say, for simple materials, which means no second gradient. So we have some assumptions for elasticity. So this is our phi delta is a is a energy function now scaled with this delta, so the original contribution, second gradient, and the forces, and y is the deformation, which is now in W2p because of the second gradient, and then we have some standard assumptions on elasticity. So W is a continuous is continuous in the neighborhood of rotations. It's frame indifferent, and we also assume frame indifference for this contribution from the second gradient. It's a convex function, and we have some growth conditions here. So force is supposed to go to zero, so we assume something which is in infinity as a volume force. Yeah. We have some additional assumptions on viscosity. So these are the red ones, the black ones were already mentioned. So we assume again some C3 smoothness in the neighborhood of rotations times rotations, and we also assume some growth from the identity. So depending on the distance of F from SO, SOD or SO3. Yeah, and then we define a weak solution of the nonlinear system in a standard way. So we just take a test function phi and so on. So define a weak formulation of this nonlinear system. So this is just a kind of standard formulation. It's for almost every time instant, which is positive or zero. And then we have linear equations for the weak solution for a linear system. And again, this is just very similar as before. So we are looking for U satisfying the weak form of the equations. While U is just scaled like a y minus x divided by delta. Yeah, and so we were able to show that there is a weak solution to the nonlinear viscoelasticity equation, and there exists the unique solution to the linear viscoelasticity equation. So for a nonlinear system, we cannot expect uniqueness. This is quite clear, but there is a weak solution which is unique for a linearized system. And then for that, we define the global dissipation distance. So this is the one in linearized setting using the CD, so the viscosity tensor of viscosity constants, and this is a difference of gradients of the displacement. So, and the similar here for the delta. So for delta positive. Yeah. And we run the minimization problems for time-discrete settings. So we get again the sequence of solutions, but the next one is always obtained as a minimization of this function using the information from the previous solution, and then we use a piecewise constant interpolation and then have a discrete solution. And then we do the minimizing movements, which go back to the Georgi, but then this is just a definition, and yeah, so having some condition on the initial datum, so then we say that we denote by mm all minimizing movements, which starts from y0, coming from the minimization of phi d, and then again we define a new curve for if we just take corresponding discrete solutions into the limit above all. So this is now called generalized minimizing movement. So this is just a special if there exists a curve like this. Now this is the main result. What we have is that if you take a sequence of deltas going to zero and some sequence of initial conditions such that they satisfy these conditions, then if you have a unique solution to the system of linearized viscoelasticity, then you have the following convergences. So here you take fixed time increment and you drive delta k to zero. So this goes to time discrete solution of the linearized system. And then if you take a sequence yk which satisfies this, then you get a strong convergence to the solution, time continuous solution of the linearized system. But you also can go diagonally, so you drive time step to zero and also delta to zero, and again you get a convergence to the to the solution of the linearized system. So you can go all ways and also diagonally. Yeah, and so the idea is that you also have a gamma convergence of the functionals. So the functional with delta positive are gamma convergence to the system, to the functional for the linearized viscoelasticity with respect to the weak H1 convergence, which is, and the functionals are defined here. So this is in fact the result. So the sequence of functionals gamma converge to the functional for the linearized viscoelasticity, and then you can even may have an improved convergence for a sequence. So this is true. So for example, you can use the results by Dalmaso and Negri-Percivale for the lower bound. This is the main contribution, and the proof of the upper bound is first done for smooth maps and then extended. So we have the following convergences. And then if you have the convergence of functionals, which is for the recovery sequence, then you even have a strong convergence of solutions, and this is because of the, strict convexity of the functionals. So it's an improved convexity by using the convergence of energies and weak convergence of solutions. So the main tools is gradient flow in metric spaces due to Ambrosio-Gilles-Savare, and also rigidity estimates by Friedrich, James, and Miller, which is already used by Dalmaso and Negri-Percivale just to show the linearization of normal elasticity. And so let me summarize a little bit. So we found a solution to non-simple hyperelastic Kelvin-Voigt materials. So non-simple means there is a second gradient in the elastic energy present, and currently we don't know how to avoid this. So without it, we cannot proceed, and this is already observed by other people. So I don't know if there is some technique now to avoid this. But at the end, we show that the small strain limit satisfies the linear viscoelasticity equations, and because we have a solution for a standard viscoelastic linearized system, starting from, say, non-simple material, which means the second gradient is present, then I would a little bit just like to state that I believe this is a kind of justification of these non-simple elastic materials, because at the end you get something what is expected. You also don't have to do it, so if you want to get a system which has a strain, it's a gradient of the linearized strain tensor, we can also keep this coefficient in front of the second gradient fixed, and we get a kind of linearized system which has a gradient of P of U. But we didn't want to do that. Yeah, and there are some references. So this work was published last year in Science Journal of Mathematical Analysis, and if you want to learn more about these approaches in elasticity via B-clover semi-continuity and so on, so there is a review paper which we have written with Barbara Benešová. It's called B-clover semi-continuity of integral functional and applications, and it appeared in November 2017 in Science Review. Thank you very much for your attention.
Is there some sort of uniqueness for your initial, for the model with epsilon?
No.
No. You expect?
No, I don't expect. No.
There's a very recent paper which I have not read by Sheng Yang. Have you seen this? On where he claims to use convex integration for the for polyconvex gradient flows and same equation, and claims to get, well, I'm not sure about existence, but anyway, lots of non-uniqueness for the initial value problem.
Okay. No, I didn't.
Don't know what.
So maybe I can just ask you for reference.
It's in the archive, I just checked.
Okay.
I have a very technical question. I don't quite understand why the dissipation distance is in GL3. Why is in general linear group?
Because we want to work with GL3 is like
Why your F1, F2
are positive
both,
determinant?
yeah, are both in GL3?
Because these are for me like placeholders for gradient of y, and the gradient of y is some gradient of a deformation, and I assume that this is orientation preserving, so I want to have positive determinant. I mean, if I skip this assumption, then I can also do that, and many people do that, but I don't think it's a really, because I mean, positive determinant means you don't go, your body cannot go upside down.
Yeah,
so
that's okay, but GL3, as far as I know, is determinant equals 1. Right?
No, this is SL.
Oh, SL
This is special linear group.
Okay.
So the determinant doesn't have to be 1. This is not incompressible, it's just compressible material.
Okay, another question is, if we want to do like linearization thing, why don't we just consider the stretch part? Like we do f transpose f, we get Cauchy-Green tensor, and then we do the square root of that.
Which part it would be?
I mean, why we write everything in terms of deformation gradient and first of Euler-Kolkov? Why don't we just use small strain and Cauchy tensor, which is also a energy conjugate.
Yeah, but small
and
strain.
then we do strain dots, right? Strain dots with Cauchy stress.
So first of all, the small strain I don't want to use from the beginning because I want to have a nonlinear model in the beginning. This is my starting point. And yeah, I don't know, I mean, in solid mechanics.
This is like you want to linearize something.
Yeah.
You have like a deformation gradient first, and then you add the time term, and then you add the second gradient of the deformation, and then you do linearization in the end. Then I don't understand why don't we just use linearize the strain and that strain dots?
Because I wanted to verify that the linearized equations are the correct ones. So that there are not two models which are in parallel, completely independent, but that you can get one from the other by looking at, deformation gradients around identity or deformations around identity.
Okay.
So that was the main reason for it.
So it's just another sort of general remark. I'm sure you've thought about these same things, but you're adding second gradients in order to get some extra compactness. But I mean, the belief, I suppose, among some people, I don't know whether you saw these papers of Ribka many years ago, where you had a non-frame indifferent viscoelasticity, term Laplacian of the okay, well, it's not frame indifferent, but still one believes that dissipation is strong enough to handle non-convexity in the elastic energy, and that would be. So we look of course for some kind of dynamical equations that would describe phase transformations, and that's a sort of kind of candidate, without.
Oh yeah.
Because if we had second derivatives, that introduces other sort of physical issues.
Yeah, I mean, if you at inertia, then it's,
But it seems that you have to somehow, you're using this rigidity, but I mean, the sort of rough calculations you do suggest you somehow have to, it's easy to control the strain when you're trying to prove this, or reasonably easy to control the strain, but it's controlling the rotation. So somehow you need to integrate something up from the initial data, maybe using rigidity estimates or something like this, to try and, if one was going to manage to prove existence. So any other questions? Okay, so we can stop. Thank you very much.